Good evening. Wonderful to see this crowd for our third lecture of the Great Brown Nonfiction Writers Lecture Series. And this evening we are honored to have Alan Lightman, who at the same time we're honored to have him teaching here this spring. He's teaching a master class in the essay in the Nonfiction Writing Program. And as many of you know, Alan is an essayist, a novelist, a physicist. He has a PhD in theoretical physics. He's currently professor of the practice of the humanities at MIT, and he was the first person there to receive dual faculty appointments at MIT in both the sciences and the humanities. His essays and articles have appeared in Harper's, The Atlantic, New Yorker, Granta, other publications. His most recent book, The Accidental Universe, has just come out. His previous award-winning books include a collection of essays, one called A Sense of the Mysterious, another book called The Discoveries, Great Breakthroughs in 20th Century Science. Most of you, I think, know his novel Einstein's Dreams, which was an international bestseller and has been translated into 30 languages. He also has a novel, The Diagnosis, and the novel, Mr. G, about the creation as told by God. He was elected as a fellow of the American Academy of Arts and Sciences and has won numerous awards and has been the recipient of 4 honorary doctorate degrees. He is also the founding director of the Harpswell Foundation, whose mission is to empower a new generation of women leaders in Cambodia. So I often use Alan to get going with some of my essay classes by quoting from his wonderful introduction to the best American essays of the year 2000. So just a couple of the things that he said in that essay that I'd like to read, and I'm hoping he will speak more towards this evening. So Alan says, "For me, the ideal essay is not an assignment to be dispatched efficiently and intelligently, but an exploration, a questioning, an introspection. I want to see a mind at work, imagining, spinning, struggling to understand." Later he says, "When I'm reading a good essay, I feel that I'm going on a journey. The essayist is searching for something and taking me along. That something could be a particular idea, an unraveling of identity, a meaning in the wallow of observations and facts." And finally, a little bit later, he says, "I suppose that in the end, the real subject of an essay is the essayist, not the bald facts of autobiography on the one hand, or the bald opinions about issues on the other, but some kind of union between the inner person and the outer world, a melding of internal and external, the life and mind of the essayist in reaction to the universe." So this evening, Alan will talk about his own writing process. Alan?
Thank you, Beth. I want to thank Beth Taylor and Larry Stanley for inviting me to Brown this year to teach in the nonfiction program. I'm enjoying it tremendously. I've always loved Brown students. My oldest daughter, Elise, was a graduate of Brown, class of 2002. And I got to know her classmates when she was here. I admire the Brown students not only for your smarts, but for your independence and your resourcefulness and your engagement with the world. So I'm very happy to be here and honored to be part of the great nonfiction writers series. I think there's another adjective in there as well, but so that's enough. So I'm here tonight to talk specifically about science writing, not writing in general, but science writing. And I wanted to start with reading a little snippets of a piece that I wrote for the New York Review of Books a few years ago. Until the age of 7 or 8, whenever the young Albert Einstein was asked a question, he would slowly formulate an answer, mutter it tentatively to himself, and finally repeat aloud his considered response. This laborious method of speaking gave the impression that he needed to say everything twice. His parents consulted a doctor, and the family housekeeper called the boy stupid. Decades later, Einstein's sister, Maya, recorded this odd childhood habit and attributed it to her brother's thoroughness in thinking. Yet the doubling of each sentence, once for himself and once for everyone else, may also have been an early sign of the deep inner world that Einstein inhabited. Brilliant, supremely self-confident, brutally honest, witty, stubborn, Einstein was, above all else, a loner. The Nobel arrived in 1921, and I guess Einstein was around 42 or so. At that time, a journalist gave the following description of Einstein. Einstein is tall, about 1.7 meters, with broad shoulders and a scarcely bent back. His head, the head in which the science of the world was newly created, instantly attracts lasting attention. A little mustache, dark and very short, adorns a sensuous mouth, very red, rather big, with its corner betraying a permanent slight smile. But the strongest impression is that of stunning youthfulness, very romantic, and at certain moments irresistibly reminiscent of the young Beethoven, who, already marked by life, had once been handsome. And then suddenly laughter erupts and one is faced with a student. End quote. At the turn of the century, when the young Einstein began crafting a theory of special relativity, physicists knew of two fundamental forces of nature, the gravitational force and the electromagnetic force. Einstein did not initially set out to propose new concepts for time and space, but rather to explain a particular problem in the theory of electromagnetism. And the problem was this. During the last decades of the 19th century, physicists had shown that light consisted of undulating waves of electrical and magnetic energy traveling through space. All known undulations of energy, such as sound waves, required a material substance to traverse. For example, when sound travels across a room, it is the air molecules in the room bumping successively into one another like a row of falling dominoes that constitute the traveling wave of sound. Sound can travel through a gas, a liquid, or a solid, but it cannot travel through a vacuum. It needs the dominoes. By analogy, scientists assumed that the propagation of light required an underlying material substance. This substance was called the ether. Furthermore, the ether, a gossamer and practically weightless material, was required to fill up every nook and cranny of the universe, since the received light of distant stars clearly showed that light could travel through the vast reaches of space as well as across a living room. Now, it's both intuitively obvious and also true that sound will travel more quickly across a room if it does not ride on static air, but on a wind blowing through the room. By analogy, physicists assumed that the speed of light would depend on the motion of the ether going past the observer, or the observer going past the ether. The great quandary was that all attempts to measure the motion of an observer through the ether had proved unsuccessful. Light rays seemed to travel at the same speed regardless of which way the assumed ether wind was blowing. The ether's physical reality had never been confirmed. Einstein postulated that it didn't exist, that it was superfluous. Without an ether, it could not be said that an observer was moving or not with respect to the ether. In fact, it couldn't be said that an individual observer was moving at all in absolute terms. By postulate, Einstein had eliminated the cosmic frame of reference against which all individual motions could be measured. Only the relative motion of two observers, or any two things, had meaning, hence the name relativity. Well, that's the most technical thing that I'm going to read to you tonight. So if you're worried, you don't have to worry anymore. I wanted to talk to you tonight about some of the challenges and the techniques in writing about science. And I'm going to read from some of the writing of great science writers. But first, let's talk just a moment about why should we write about science at all? Well, first of all, science is part of our cultural heritage. If a person had not read any of the plays of Shakespeare or had not listened to any of the symphonies of Beethoven, we would consider that that person was missing out on some of the great achievements of fellow human beings. And likewise, a person would be missing out, would be deprived if they knew nothing of the idea of natural selection or nothing of the second law of thermodynamics. So science is is one of the great achievements of human beings. It's also a powerful force that shapes our civilization. In fact, one could argue that science is the most powerful force today in shaping modern civilization. And we live in a democratic society, and in a democratic society, citizens have the responsibility to be informed about the major issues shaping their society. We need to know, for example, why the Strategic Defense Initiative proposed by Ronald Reagan in the early 1980s to shoot down enemy missiles with lasers mounted on satellites powered by nuclear reactors in space, why that was an impractical idea. Just a few days ago, there was a debate on Meet the Press in which two people debated climate change. Neither one of those people was a scientist, and I think this is incredible black eye and embarrassment for NBC that they had this debate, but between two people who were not scientists. But the point is that climate change is another issue which is vitally important to our world today, and we need to know something about the issues. Scientists are often interesting and influential people. You notice I didn't say always interesting, but often interesting and influential, and so we should know what their view is of the world. And finally, science can be a subject of beautiful writing, just like descriptions of a landscape or memories of a love affair or creations of characters. And I wanted to mention right at the beginning just a few of my favorite writers who write about science in some of their books. I would start with Borges and The Garden of Forking Paths, Italo Calvino and Cosmic Comics, Tom Stoppard and his play Arcadia, Annie Dillard and her collection of essays Pilgrim at Tinker Creek, Lewis Thomas and his collection of essays Lives of a Cell, Primo Levi and the Periodic Table, Rachel Carson and Silent Spring, and Jim Glick and Chaos. And I'm going to read a little bit from some of those books later on. So what are the challenges of good science writing? Well, first of all, most people, and I'm really, when I imagine a reader here reading about science, I'm not imagining a science major. I'm talking about someone with a general education, maybe a history major, an English major, but not a science major. Most educated people are not familiar with science, with the concepts and the vocabulary of science, and furthermore, most people have a fear of science. They remember with horror trying to memorize the animal kingdoms in their high school biology class, or they remember with discomfort the unpleasantly trying to calculate how much weight it takes at the end of a seesaw to balance a pile of bricks. So these are not pleasant memories for most people. There's also in science a challenge in connecting. In the arts and humanities, ultimately we're trying to connect to people. We're trying to connect to the psychology and the emotions of human beings. And in science, and the doing of science, we're trying to connect to the physical world external to our bodies. But as a science writer, you have to make both connections. And that's one of the challenges of being a science writer. And another challenge is that most science, and certainly modern science, is far more removed from the world of human sensory perception. And the best example of this is the discovery in the last 100 years that there are many wavelengths of light that are invisible to the human eye, such as radio waves and X-rays. Modern science is about a world that we cannot touch or feel or hear with our own bodies. So that is a further challenge to writing about science. And finally, there's the danger of didacticism, that no one outside of a university classroom in reading an article wants to feel like they're getting another lecture in Chemistry 101. So these are some of the challenges in writing about science. So let me talk now a little bit about the techniques in writing about science and how we face these challenges as science writers. Of course, many aspects of writing about science are the same as writing about any subject, any kind of writing at all. There's considerations of clarity. You want beauty of language. You want power and meaning in your writing. You're concerned with pacing and rhythm. So I'm not going to talk about some of the general challenges, but I want to move on to some of the specific techniques in writing about science. And in writing about science or any specialized topics such as law or economics, there are concepts that must be explained. And so if you're not a scientist yourself, and I'm assuming that the science writer is not a scientist themselves, then what I recommend is that you develop a stable, professional physicists, chemists, biologists, astronomers whom you can call up and learn from and talk to. Get their email addresses, get their phone numbers. Some of our greatest science writers were not scientists themselves, like Jim Glick and Annie Dillard and Natalie Angier, but they're smart people and they know how to find out what they don't know. And you shouldn't be shy about talking to these experts, but you should keep asking them over and over and over to explain it to you in different ways until you really understand it. And if you don't understand it thoroughly, your reader will not understand it. So that's one of my first recommendations. Well, you have to establish your authority, and in fact, you have to establish your authority in any piece of nonfiction writing. So how do you establish your authority if you're not a scientist yourself? Well, you show the reader that you've done your homework. You do that by having lots of good thinking, lots of facts, and reference some leading scientists that you've talked to. And there's also something that's very, very important in showing your authority, and this really applies to all nonfiction writing about a technical subject, and that is that you need to understand the material one level deeper than what you're writing. I can't emphasize how important this is. If you're writing right at the edge of your knowledge, then the reader will sense the thin ice and will poke through it. So you need to understand a lot more than what you're actually putting on the page. And if you have that extra depth of knowledge, the reader will sense it and they will respect your authority on the subject. Human beings need to be put into the piece in some way, because ultimately what we care about is human beings, no matter what we're writing about. And I'll tell you a story. In the early 1980s, I went to New York City, and I visited the offices of Charles Scribner's and Sons, a very venerable old publisher. I think they started in 1846. It's now run by the fourth generation, Charles Scribner the fourth. At least it was in the early 1980s. This was a tall gentleman. He must have been in his late 60s or early 70s at the time, very refined and distinguished. And I was just beginning to write articles about science myself, essays, and Scribner's published my first book. So Mr. Scribner took me first into the library, not very large, which was a wood-paneled room, and they had beautiful bookshelves there. And on the books were the books of all of the famous authors that Scribner's had published, like Ernest Hemingway, and like F. Scott Fitzgerald and Edith Wharton. Scribner's was also starting to publish some science writers. They were beginning to publish C.P. Snow at that time. So after showing me this library and intimidating me, Mr. Scribner took me to his office and sat me down and said to me, no matter what subject you're writing about, whether it's science or anything else, you have to tell a good story. That's what people want. They want to read a good story. And to make a good story, you usually need people. So it's very good form as a science writer to anchor your piece in the profile of a scientist, one of the major scientists that's doing the science that you're writing about. There'll be plenty of room to talk about the science itself and the history of the subject, but you need to anchor it in a particular person. And I was just looking at the science section of the New York Times today, and there's an article here on new research on the brain and how we measure the change in neurons when we're learning things. And the story starts off when Clay Reed decided to leave his job as a professor at Harvard Medical School to become a senior investigator at the Allen Institute for Brain Science, blah, blah, blah. It anchors the story from the very beginning in a particular scientist, and they keep coming back to him. That's good form in science writing because we care about that individual person and we see the world of science through that particular person. Good metaphors and analogies are extremely important in writing about science and any technical subject. In the late 1920s, scientists discovered that the universe is expanding, but there's no center of the expansion. Every point of the universe is equivalent to every other point. So how do you convey a concept such as expansion but no center to the expansion? It seems like that's a contradiction. Well, in the mid-1930s, the astronomer Arthur Eddington, the British astronomer, came out with this wonderful metaphor. Imagine putting ink dots on a balloon, and each ink dot is to represent a galaxy. And then imagine blowing the balloon up. Well, as the balloon is being blown up, from the point of view of any one ink dot, all the other ink dots are moving away from it. And yet, there's no center of the expansion because the view looks the same from any ink dot. So there is a very vivid metaphor that allows us to understand what it means to say that you can have expansion without a center of the expansion. Here's how the science writer Richard Preston described the workings of a smallpox virus in an article that he wrote for The New Yorker in 1999. Quote, "Inside the cells of the host, smallpox bricks pile up as if they were coming off a production line. The tailed smallpox particles look like comets or spermatozoa. Then something wonderful happens. Finger tubes begin to extend from the infected cell. The tubes grow larger. The cell turns into a cush ball. Inside each finger tube is a smallpox comet. The fingers lengthen until they touch and join nearby cells, and the smallpox comets squirm through the finger tubes of the next cell to the next cell. How many of you have seen Kush balls? Well, not as many as people as I thought. So if most of you have not seen a Kush ball, then that's not a very good metaphor to use. You need to use metaphors that people are familiar with. I have seen lots of Kush balls, and I thought that everybody else had as well. So I've learned something tonight at this lecture. Anyway, if you've seen a Kush ball, or if you've seen an assembly line or some of the other images and metaphors he uses there, it really helps you visualize what's going on. Here's another example of an analogy or a metaphor, a picture. I was writing an article some years ago, and I had to use the speed of light, which is 186,000 miles per second. Now, how do you convey such an enormous speed? Well, I thought of trying to convey it by a distance that light could travel in a second, but how do you convey a distance as big as 186,000 miles? The largest distance that we have any intuition for is the Earth, the size of the Earth. So I use this metaphor. If you put an array of mirrors around the Earth and you deflected a light ray so that it could go in a circle and bounce around those mirrors in a circle, it could go around the Earth 7 times in 1 second. So that kind of conveys the speed. That's what I'm talking about in finding metaphors. I once was trying to describe the nucleus of an atom in comparison to the size of the atom as a whole. The nucleus is this tiny little thing that sits at the center of the atom. It's 100,000 times smaller than the atom as a whole. So to convey this ratio, 100,000 times smaller, I started, well, I'll let something big represent the atom. And so what's a big object that most people know? You need to use in your metaphors things that people know, and I'm very sorry that most of you didn't know the Kush ball, which shows that Dick Preston didn't do his homework when he used that metaphor. Well, I live in the Boston area, and a very big thing there is Fenway Park. Have any of you been to Fenway Park? A few more there. A few more than who know Kush balls. Have any of you been to Yankee Stadium? Okay. Well, Fenway Park is a big space, and you can look it up. You can Google it. It's about 600 feet across if you haven't measured it yourself. So I'm going to use Fenway Park as my big object. Now I want something that's 100,000 times smaller. So I'll divide 100,000 into 600 feet, and I get a little bit less than 1/10 of an inch. So now I'm looking for an object that's about 1/10 of an inch. So I begin thinking, well, seeds are pretty small. And I go to the internet again, and I find that a poppy seed is about the right size. So now my metaphor is complete. I can say that the nucleus of an atom to the whole atom is about the same as putting a poppy seed at the center of Fenway Park. And that completes the picture. You can see that in your mind, and it conveys this large ratio between the atom as a whole and the nucleus at its center. I'm sort of taking you through my own train of thought in creating metaphors and analogies. I'll give one more example of the numerical analogy. And I should say that the numerical analogies are particularly important when you're talking about very large numbers or very small numbers. These are the things that are hard for people to visualize. So you have to relate large numbers or small numbers to objects and things that people are familiar with. So let me give you one more example. I gave you the nucleus of the atom, the speed of light. Suppose you want to convey a volume. Now, we've been worried about terrorist attacks, and we've been particularly worried in the last 10 years about bioterrorist attacks. The world is free of the disease smallpox right now. No one has any immunity to it because it's been wiped out, except there are a few laboratories in the world, including Russia, that have been cultivating smallpox as a bioweapon. Suppose that a smallpox attack was done on the United States. We would need about 100 million doses of vaccine to protect the public from that, to keep it from growing rapidly. The volume of one dose is about is 1/3 of a cubic centimeter. So you need about, you have a total volume of smallpox vaccine of about 33 million cubic centimeters. How do you convey that size or that volume or that number? 33 million cubic centimeters. Most people can't visualize that. Well, I want to first convert that to a linear dimension so I can visualize it. So I take the cube root of it, which you can do with your scientific calculators, and I get a linear dimension of about 10 feet. That's the cube root of 33 million cubic centimeters, 10 feet. Well, 10 feet is about one side of a one-car garage. So I can say that you could put the vaccine needed, you could store the vaccine needed to immunize the United States in a one-car garage. And that the reader can visualize. So let me move on to another aspect of science writing, and then I'm going to read you some good science writing. Pacing. Pacing is a more advanced element of good writing. How long individual sections of your article are, how you switch back and forth between different kinds of material in your article. That's called pacing. And I have a 150-word rule that I try to use for myself and for my students in science writing. And the rule is that you don't have more than 150 words straight of pure science. If you have a lot more than that, the reader begins to fall asleep, even if it's very vivid science writing. Let me read you a 150-word paragraph from David Quammen, who wrote an essay about an astronomer named Tycho Brahe, who, among other things, was the first person to discover a supernova. A supernova is an exploding star. So let me read you a paragraph that's about 150 words. And Quammen is one of my favorite science writers. Have any of you read David Quammen? A few people? Good. Quote, "It was a supernova explosion. Only 5 such cataclysmic events have been visible from Earth during the past 1,000 years, and of those, Tycho Brahe's in 1572 was the 4th. Some thousands of years earlier, a gigantic star, much larger than our sun, had come to the end of its lifespan. The hydrogen nuclei at its core all burnt by fusion to form helium nuclei, and the helium further fused into still bigger nuclei. The star had then fallen into a terminal sequence of convulsions, alternately expanding and contracting, gravitational compactions seething down against rising internal pressures, which led to a final, incredible thermonuclear explosion. That explosion flared out perhaps 1 billion times brighter than the star itself had shown. And the flash, having traveled across all those light years between, eventually showed itself to Earth from the direction of Cassiopeia. Then, by 1574, it was gone. No one knew why, not even Tycho Brahe." And note the vivid language, the strong nouns and verbs in that piece of writing. Notice also that Quammen explains some things but not other things. He explains the balance between the gravitational force and the internal pressure, but he doesn't explain what a helium nucleus is. He doesn't explain what a light year is. And that's part of the art of science writing, to know what to explain to the reader in your writing and what to leave unexplained. I call it an art because there are no hard and fast rules. You just have to experiment, trial and error, and decide how much explanation you should give. I usually do not explain technical terms if the reader can get them by context. And finally, there's the technique of alternating between different kinds of material. If you're writing an article about science, especially a long article, say 3,000 words or longer, you're going to have several different kinds of material. You're going to have the science itself. You're going to have the biography of the scientist. You're going to have the history of the subject. You're going to have the larger meanings of this science for the world at large. You might have some personal commentary. So you've got at least 5 different kinds of material. And the most artful way to write the long article is to alternate between these different kinds of material, keep coming back to one, then going to another, coming back. You don't just have all the science in one spot, all the biography in one spot, all the history in one spot. You sort of weave back and forth between the different kinds of material, and that is most engaging to the reader and is the most artful way to write a long nonfiction piece. Well, let me give you a few examples. When should we be done by? 7:30? Yeah, okay, 7:30. Okay. I want to read a little snippet of Silent Spring, which is a book. It started as a New Yorker article, a book written by the biologist Rachel Carson in 1962, published in 1962. And this was really the beginning of the environmental consciousness and the environmental movement in the United States. I mean, this shows how powerful a piece of writing can be, that you can launch a whole movement. And in this piece, I'm going to read the opening chapter. There are no people in it, so it violates my rule of having a profile of a person, but she does paint a scene of a fictitious town very beautifully and with lyrical writing. There was once a town in the heart of America where all life seemed to live in harmony with its surroundings. The town lay in the midst of a checkerboard of prosperous farms with fields of grain and hillsides of orchards where in spring white clouds of bloom drifted above the green fields. In autumn, oak and maple and birch set up a blaze of color that flamed and flickered across a backdrop of pines. Foxes barked in the hills and deer silently crossed the fields, half hidden in the mists of the fall mornings. Along the roads, laurel and alder, great ferns and wildflowers delighted the traveler's eye. Even in winter, the roadsides were places of beauty where countless birds came to feed on the berries and on the seed heads of the dried weeds above the snow. Then a strange blight crept over the area and everything began to change. Some evil spell had settled on the community. Mysterious maladies swept the flocks of chickens. The cattle and sheep sickened and died. Everywhere was a shadow of death. The farmers spoke of much illness among their families. In the town, the doctors had become more and more puzzled by the new kinds of sickness appearing among their patients. There had been several sudden and unexplained deaths, not only among adults but even among children, who would be stricken suddenly while at play and die within a few hours. There was a strange stillness. The birds, for example, where had they gone? On the farms, the hens brooded, but no chicks hatched. The farmers complained that they were unable to raise any pigs. The litters were small, and the young survived only a few days. The apple trees were coming into bloom, but no bees droned among the blossoms. There was no pollination, and there would be no fruit. The roadsides, once so attractive, were now lined with brown and withered vegetation as though swept by fire. Even the streams were now lifeless. Anglers no longer visited them, for all the fish had died. No witchcraft, no enemy action had silenced the rebirth of new life in this stricken world. The people had done it themselves. And here, I think what I wanted you to note is that the writing has emotional impact, that even science writing can have emotional impact. And she's really not giving you lots of facts here. She's not telling you how many cubic tons of DDT have been dropped on farms and in the air. She's trying to appeal to your emotions and to engage you in the subject emotionally. Of course, there are many other later chapters in the book where she does give you lots of facts and figures. Let me read you a little section from Jim Glick's book, Chaos, published in 1987, which was the first popular exposition of a new science. And Glick focuses on a particular scientist who was involved with this. The sun beat down through a sky that had never seen clouds. The wind swept across an earth as smooth as glass. Night never came, and autumn never gave way to winter. It never rained. The simulated weather in Edward Lorentz's new electronic computer changed slowly but certainly, drifting through a permanent dry midday mid-season as if the world had turned into Camelot or some particularly bland version of Southern California. Outside his window, Lorentz could watch real weather, the early morning fog creeping across the Massachusetts Institute of Technology, or the low clouds slipping over the rooftops from the Atlantic. Fog and clouds never arose in the model running on his computer. The machine, a Royal McBee, was a thicket of wiring and vacuum tubes that occupied an ungainly portion of Lorentz's office. Yet Lorentz created a toy weather in 1960 that succeeded in mesmerizing his colleagues. Every minute, the machine marked the passing of a day by printing a row of numbers across a page. He was the god of this machine universe, free to choose the laws of nature as he pleased. After a certain amount of undivine trial and error, he chose 12. They were numerical rules, equations that expressed the relationship between temperature and pressure, between pressure and wind speed. Lorentz understood that he was putting into the practice the laws of Newton, appropriate tools for a clock master deity who could create a world and set it running for eternity. Thanks to the determinism of physical law, further intervention would then be necessary. Understand the laws and you understand the universe. That was the philosophy behind modeling weather on a computer. And of course, the punchline of all of this is that you can't really model weather on a computer because very, very slight errors in the initial conditions will produce large changes in the end, and that's the whole idea of chaos. That's what Glick's book is about. But this is a very gripping section. It also gives you a feeling for the fascination of the people involved and for Edward Lorenz in particular. So I want to read you a little piece of one of my own essays. This is called The Temporary Universe, which was first published a couple of years ago in Tin House. The title is The Temporary Universe. Last August, my oldest daughter got married. The ceremony took place at a farm in the little town of Wells in Maine against the backdrop of rolling hills a white wooden barn, and the sounds of a classical guitar. Each member of the wedding party stepped down a sloping hill towards the chuppah, while the guests sat in simple white chairs bordered by rows of sunflowers. The air was redolent with the smells of maples and grasses and other growing things. Radiant in her white dress, a white dahlia in her hair, my daughter asked to hold my hand as we walked down the aisle. It was a perfect picture of utter joy and utter tragedy, because I wanted my daughter back as she was at age 10 or 20. As we moved towards that lovely arch that would swallow us all, other scenes flashed through my mind. My daughter in first grade holding a starfish as big as herself. My daughter on the back of my bicycle as we rode to a river to drop stones in the water. My daughter telling me the day after she had her first period. Now she was 30. I could see lines in her face. I don't know why we long so for permanence, why the fleeting nature of things so disturbs us. With futility, we cling to the old wallet long after it has fallen apart. We visit and revisit the old neighborhood where we grew up, searching for the remembered grove of trees and the little fence. We clutch our old photographs. In our churches and synagogues and mosques, we pray to the everlasting and eternal. Yet, in every nook and cranny, nature is screaming at us at the top of her lungs that nothing lasts, that it is all passing away. All that we see around us, including our own bodies, is shifting and evaporating and one day will be gone. Where are the 1 billion people who lived and breathed in the year 1800, only 2 short centuries ago? The evidence seems overly clear. In the summer months, mayflies drop by the billions within 24 hours of birth. Drone ants perish in 2 weeks. Daylilies bloom and then wilt, leaving dead, papery stalks. Forests burn down, replenish themselves, then burn down again. Ancient stone temples and spires flake in the salty air, fracture and fragment, dwindle to spindly nubs, and eventually dissolve into nothing. Coastlines erode and crumble. Glaciers slowly but surely grind down the land. The sun is depleting its nuclear fuel. And just look at our own bodies. In the middle years and beyond, skin sags and cracks, eyesight fades, hearing diminishes, bones shrink and turn brittle. Physicists call it the second law of thermodynamics. It is also called the arrow of time. Oblivious to our human yearnings for permanence, the universe is relentlessly wearing down, falling apart, driving itself towards a condition of maximum disorder. It is a question of probabilities. You start with a situation of improbable order, like a deck of cards all arranged according to suit, or like a solar system with several planets orbiting nicely around a central star. Then you drop the deck of cards on the floor over and over again. You let other stars randomly whiz by your solar system, jostling it with their gravity. The stars become jumbled. The cards become jumbled. The planets get picked off and go aimlessly wandering through space. Order has yielded to disorder, repeated patterns to change. In the end, you cannot defeat the odds. You might beat the house for a while, but the universe has an infinite supply of time and can outlast any player. A little bit more? Yes. Okay. I'll say, I'm going to end by saying a few words about the difference between fiction and nonfiction, because I write fiction as well. Some of my fiction is about science and some of it isn't. So I'll just say a little bit there and read you just a little bit. In fiction, you are not striving for clarity. You are striving to create an imaginary world and to bring your reader into that world. One good distinction between fiction and nonfiction is in the topic sentence. That we all learn in high school expository writing that it's great form to start every paragraph with a topic sentence. A topic sentence names the idea of the paragraph. It tells the reader how to organize her thoughts before she's about to read the paragraph. In fiction, a topic sentence is fatal because in fiction, you want to bring your reader into that imaginary place. You want your reader to feel and be part of the scene, and telling your reader right at the beginning how she's supposed to think about the experience totally cancels the trip. So you don't use topic sentences in fiction. One more difference I'll mention is that in fiction, as opposed to nonfiction, you have to be willing to surrender control to your characters. In nonfiction, you can organize your material, you can do research, you can make an outline, you kind of know where you're going. In fiction, if you overplot your characters, they will never come to life. So you have to give room to your characters to come to life and to live and breathe, and for that, they have to be able to surprise you, the author. So you can't overplot your characters. You've got to create them and then just follow them. So it's a very nervous process for someone who's trained as a nonfiction writer. And when I first began writing fiction, I started a lot of paragraphs with topic sentences and made a lot of mistakes. So let me end by just reading a snippet from a fiction that I wrote. It's part of my book, Mr. G. And as Beth Taylor said at the beginning, this is a novel that is the story of creation as told by God. God is the narrator. God has an aunt and an uncle who are constantly giving him advice about how to do things. Once God starts creating time and space and planets and stars and living beings, then a lot of science comes into it. So there is science in the book, and one of my purposes of writing the book was to have a kind of a playful dialogue between science and religion. So I'm going to read you just a tiny bit from the beginning of that book. As I remember, I had just woken up from a nap when I decided to create the universe. Not much was happening at that time. As a matter of fact, time didn't exist, nor space. When you looked out into the void, you were really looking at nothing more than your own thought. And if you tried to picture wind or stars or water, you couldn't give form or texture to your notions. Those things didn't exist. Smooth, rough, waxy, sharp, prickly, brittle, even qualities such as these lacked meaning. Practically everything slept in an infinite torpor of potentiality. I knew that I could make whatever I wanted, but that was the problem. Unlimited possibilities bring unlimited indecision. When I thought about this particular creation or that, uncertain about how each thing would turn out, I grew anxious and went back to sleep. But at a particular moment, I managed, if not exactly to sweep aside my doubts, at least to take a chance. Almost immediately, it seemed, my Aunt Penelope asked me why I would want to do such a thing. Wasn't I comfortable with the emptiness just as it was? Yes, I said. Of course, you could mess things up, said my aunt. Leave him alone, said Uncle Deva. Uncle toddled over and stood beside me in his dear way. Please don't tell me what to do, retorted my aunt. Then she turned and stared hard at me. Her hair, uncombed and knotted as usual, drooped down to her bulky shoulders. "Well," she said, and waited. I never liked it when Aunt Penelope glowered at me. "I think I'm going to do it," I finally said. It was the first decision I'd made in eons of unmeasured existence, and it felt good to have decided something. In fact, I had just created time, but unintentionally. It was just that my resolution to act, to make things, to put an end to the unceasing absence of happenings required time. By deciding to create something, I had pressed an arrow into the shapeless and unending void, an arrow that pointed in the direction of the future. Henceforth, there would be a before and an after, a continuing stream of successive events. Time necessarily came before light and dark, matter and energy, even space. Time was my first creation. "See," my aunt complained when it became apparent that we were now conscious of time. "I told you that you'd mess things up." She shot Uncle a look of disapproval, as if he had encouraged me to act as I had. And then she began an unhappy summary of the various things that she had done and not done during the immediate past, then during the past before that, and so on, back and back to the now visible chasms of time, until Uncle begged her to stop. "You should never have created the past and the future," she said. "We were happy here. You see, now I must say were, when before, oh, there it is again. It was so much nicer when everything happened at once. I can't stand to think about the future." "But don't you think we have some responsibility to the future?" I suggested. "To all the things and beings I might create?" "Nonsense," shrieked Aunt Penelope. "What a foolish argument. You have no responsibility to things that don't yet exist and won't ever exist if you could just keep your big thoughts to yourself." "But it's too late now," she went on. "I can feel time. I can feel the future." Aunt Penelope had gotten herself into one of her states, and the void twisted and throbbed with her displeasure. Gently, Uncle caressed her. For the first time ever, she responded to his touch. Her ranting diminished. Soon after, she realized that her hair needed combing, and that was the beginning of something, and probably all for the best. Thank you. Well, thank you, everyone, for coming. Yes?
Just a quick question, Ellen. The first selection you read of your own writing that begins with your daughter's wedding, what is that taken from?
That was from an essay called The Temporary Universe, which was first published in Tin House and is part of the, is in the new book, The Accidental Universe. Yeah. Yes.
Can I ask two things, where you come up with the subjects that you choose to write about, and then secondly, what your writing schedule is like, what your other responsibilities?
Well, I keep a notebook, which I think many writers do, and when I have ideas that might lead to articles or books, I'll write them down. And usually I kick around an idea for a year or so. If it's not deeply embedded in me, then it's gone after a year. You know, I don't have any interest in it. But if I still have an interest in it after a year or so, then I feel that it's something that I need to write about. And I think that's especially important with a book where you're devoting several years of your life to a project. You really need to be passionate about it. Yeah. I didn't answer all of your question. You asked me about my writing schedule. Just when I'm involved with a big project, I usually write every day, and I think all writers have different preferred times of the day. But if I don't have any other obligations, my favorite schedule is to start writing like at 9 a.m. and stop around 3 p.m. But all writers do it differently, and it just depends on what suits you. Here.
Don't you find it just a bit boring to read article after article that begins with an anecdote about somebody?
It can be, but I don't think that all articles begin with an anecdote about somebody. I know the one that I read from the Science Times did. I think the most important thing about beginning an article is to bring the reader in, to get them interested, to get them engaged. And I think that any way that you can do that is fair game. That's not fraudulent, that's related to the subject. But I think there's so many ways to write about a person. Speaking of personal anecdotes, there's so many ways to write about that I don't think it would necessarily be boring. But I guess if I read 20 articles in a row and they all started with the anecdote of a person, I might be a little suspicious. But I think that that not all articles start with an anecdote about a person, and so I haven't found that to be a problem in either my own reading or my own writing. Yes.
When you're jotting down your ideas, how do you distinguish which ideas are going to take root as nonfiction and what might be more fun as...
Oh, that's a great question. How do I know which ideas are going to lead to fiction and which to nonfiction? If it's an idea that is principally anchored in the emotions of people or the psychology of people, then I will write it as fiction. And actually, I confronted that about 10 years ago. I wrote a novel called The Diagnosis, which is about the modern American obsession with speed and money and information. And I started that as a long nonfiction article. And then I realized I'd actually written 10 or 20,000 words of a nonfiction article, and I realized that what was most interesting about this phenomena was that it was a psychological malaise that we were suffering, this obsession. And so then I turned it into a story, and it became a novel.
Most modern scientific discoveries, especially in physics, say, take place in mathematical abstractions, and science writing needs to completely remove that formal language and translate it into its connection with concrete experiences or sensory analogies. So do you think non-technical writing can describe the fascination or meaning of the mathematical patterns and symmetries themselves? And if so, are there any tools you can think of that would be useful in writing about mathematics as opposed to science?
Well, that's a great question. I think that if it's science, no matter where it starts, even if it starts in abstruse mathematics, if it's science, if it's something that connects to the physical world, then you can leave the mathematics aside and you can talk about the physicality, the materiality of the thing. String theory, for example, is is a branch of modern physics. That the main idea there is that the smallest constituents of nature are not particles, but they're vibrating strings of energy. And you can sort of talk about that like they're strings on a violin that have different notes, and the different notes correspond to different particles. And then you can talk about the scope of string theory, how it predicts many other universes, and lots of neat stuff like that. And you don't really have to talk about the mathematics, even though it originated in mathematics. If you're talking about something where the beginning and the end of it is mathematics, where it doesn't really connect to the physical universe, then you've got a real problem. Because you can't relate it to anything material. And unless your reader knows some mathematics, you can't really get into the substance itself. You could profile a great mathematician. For example, I can write about fractals and chaos. I can profile Mandelbrot, who's a mathematician who developed the idea of this very mathematical area. And but I would mostly have to give up talking about the guts of the mathematics itself. So mathematics is a very, very specialized vocabulary and language, and unless the reader, I've never tried to explain anything mathematical in my writing. So there, I think you don't have the problem in writing about physics because it connects to the material world. But it's a good question. Yep.
In that same vein, where do you find yourself drawing the line between simplification and loss of subtlety in, like, reporting on very complex topics?
Yeah. Well, that's a great question, and of course that's a lot of the art of science writing. You need to know the subject very, very well in order to know how much you can simplify it. There was a great comment that Einstein once made about trying to explain some of his science, and that is that you should simplify, I'm probably getting it wrong, but it was something like you should simplify as much as possible, but no further. But you do have to understand the subject very, very well to make accurate simplifications. Yeah.
How much do you actually think about your audience before you write your book? The Times articles, both that one and the article below it on zebra mussels this morning, clearly the Times articles are written, I mean, I found they're both interesting from a non-scientist point of view because they talk more about the scientists than they did almost about the subject matter, and yet it drew you into the subject matter.
Yeah, well, I assume you do have to think about the audience somewhat, and I assume that the audience is an educated person with a college degree, but I do not assume that they have a science background. So I assume that I'm writing to an intelligent, well-educated person, maybe a history major, an English major, but not a science major. I don't write, and my apologies for people who subscribe to Reader's Digest, I don't write for the Reader's Digest audience. I write for an audience that a little bit narrower than that audience, but still a broad audience.
You talked some about how being an expert in a field can be helpful in your writing. So for instance, you need to
Knowing experts.
Okay, or knowing experts. But
Yeah.
I was thinking, in particular, in your case, because you're a physicist, whether you had anything to say about cases where having an expertise in a field actually is a hindrance. And
Yes.
maybe in particular, it makes it difficult for you to see what's going to be interesting to.
Right. It can definitely be a hindrance. because you can assume a certain vocabulary and level of understanding concepts that your reader may not know. So when I first started writing about science, I would let my non-science friends read everything before I sent it off for publication. And over a period of 2 or 3 years, I learned about how much I could assume on the part of the reader, how much knowledge. And after that, I knew where that line was. But I had to start by letting non-science. Are you a science major yourself? I am. Okay. So what I strongly advise is that you let your non-science friends read your stuff and give you feedback. And that way you'll find out what you can assume on the part of the reader and what you cannot assume. There's no way to get it just from theorizing in your armchair. You've got to try it out on people. But after, doing that.
Stable of physicists and chemists, you have a stable of ordinary people to try.
I certainly do. Yeah. My wife is my first reader. And she's gotten to be a better and better critic of my writing. So I do have a group of non-science friends who will allow me to inflict my writing on them. And one more question? Yep.
So it seems like most of your writing is come in the form of essays and books and more long-form pieces, but we're at a time where a lot of science communication is, lives on the internet in small bursts and different stories are being told. And I was wondering how you think, what you said today fits in there, and what you think of where science writing is going today.
Well, I think that that a lot of what I've said today would be applicable to the internet. One thing that I said that wouldn't be so applicable is alternating between different groups of material when you have something long, because you don't write long things for the internet. So you have to be more concentrated and concise for the internet, but using good metaphors and analogies, using numerical analogies, anchoring your piece in a person, I think all of those techniques apply for writing on the internet as well. One thing I didn't say anything about is using hypertext, using images to illustrate, which would be additional features of internet writing. That's a whole nother conversation, but of course you have those tools available on the internet. You can have links, you can have lots of wonderful pictures, and so that is a whole art in itself about how to do that.